Thanks everybody for joining. So this is going to be CKB programming with the cell model in scripts, and this is the first of 3 different sessions. I know Tanner has a couple more coming up that go a lot more into the details here, and this is intended to kind of set the foundation for that. And this is structured in going through basic concepts, approaching things from a standpoint of Ethereum because it's commonly understood and familiar to a lot of people, and then kind of transitioning those concepts over to programming with CKB. And the first thing I want to discuss is the state model. So the state model in Ethereum is the account model. It's very simple, straightforward. A lot of people understand it. It really is just addresses and balances. So we can see here, Alice, Bob, Charlie all have addresses. They all have balances. And every address or every account has these fields, balance, nonce, and if it's a smart contract account, has code and storage as well, which allows for data to be stored and for self-executing code. And the state of Ethereum is made up entirely of accounts. So whether it's an externally owned account, say for Alice or Bob, or an ERC20 contract or a DApp, everything is accounts. And it's the same fields that are, storing data for every account. Even on ERC20 contracts creating tokens, we see the same pattern, just different addresses, different balances. And a smart contract in Ethereum contains all of the data that is related to that portion of the application. Whatever is on that contract is kind of a single container for all of the data and everything that you need to interact with that contract. So we see here, there's a data structure built in. So all of the data that is stored on this contract is mapped out. And also we have interfaces designed to pull data out of the contract. So a lot of smart contract developers are used to this. Makes it very simple to just pull data out of the contract. And then we have transactions as well. And this is referred to as an on-chain computation model. And it makes the job pretty easy on the developers. They can just send a request to the contract. So we see here, there's a request for moving tokens to, from one address to another, a certain number of tokens that are subtracted from one address and added to another. Now, if we move over to programming for CKB, this is the cell model and a paradigm of off-chain computation and on-chain verification. And there's all sorts of performance and sustainability reasons to do things this way. But this is intended to give you an understanding of how it works. And I think there's a lot of information out there for why this is the chosen approach. And we can also refer to this as transaction generation and transaction validation. Now, analogous to Ethereum's account is the cell in Nervos. So you can see all of the state on CKB is stored in cells. And this is just a simple representation of owners and their native tokens. And we're going to do a transfer where Alice is going to move 75 CKB to Bob. Now, Alice will take her cell for 100 CKB and split that cell into 2 new cells, one for 25 for herself and one for 75 for Bob. Now, once that transaction is confirmed, the cell for 100 CKB is now moved to the historical state. And you can see on the left here, these are all the cells that are in an active state and are the current state of the ledger. Now, this presents some challenges to working with CKB in, I guess, in a manner like what we're used to with Ethereum. So if we wanted to find out, say, Alice's balance, we see here that Alice has 2 cells. We couldn't just have a simple function call that returns that Alice has 650 CKB. And we call this cell collection. So there needs to be a service that runs that collects all of the cells that meet a certain criteria, say the cells that have this certain owner of Alice. And now I'll go into how state transitions work, comparing Ethereum to Nervos. So on Ethereum, the state transitions are outlined in the contract, and anything that touches this contract will conform to this state transition logic. Now, on CKB, because the state for different owners is separated into different cells, we need a means of connecting these cells together to provide analogous functionality to that smart contract. So all of these cells need to be governed by the same logic. And we can see here toward the bottom of the screen, the logic that would govern any cell is stored in its own cell. And then we need a reference between the cell that has the logic and the cells and the cell that will be governed by the logic. And this is done through storing a hash of that logic in the cell that will be governed by it. So we can see here, Alice's cell, has a hash of the logic that is toward the bottom of the screen. And if we add this logic to all of these cells, now we have something that is similar to, say, a contract in Ethereum where all of these cells are being governed by the same logic. So now I'll go into the fields of a cell. So every cell has 4 fields: a capacity, data, a lock script, and a type script. And as we're going through this, I'm going to be updating this example so it's a little more clear as far as what these fields are doing. And I guess if anyone has any questions at any time, or if anything could be clearer, please just stop me and chime in. And I guess I'll go from here. All right, so the first field is the capacity field. So in some ways, this is similar to the amount of a Bitcoin UTXO. So it is a monetary value of sorts that can't be double spent, but this is also a measure of storage on the ledger. So all of the fields that are a part of a cell cannot exceed the amount of the capacity. So capacity is measured in bytes. Say if we have a cell that has a capacity of 1000 CK bytes, all of the fields that are contained in that cell, all 4 of the fields that I outlined before, even the value of the capacity itself has to fit into those 1000 bytes. And here we'll update the example showing that the single owner has 20,000 CKB and the multi-owner has 80,000. Now the data field is very flexible. You can store any kind of data you like in those fields, in the data field, and that is to support any sort of application you might create. So a simple example would be, say, storing the number 1000 in the data field. So as we get into simple UDT, you could see something simple like this, like just a number stored in the data fields. Or we could store compiled code in the data field. So anytime you're using scripts, those will be cells that have compiled code in the data fields. The next thing I want to talk about is this concept of a lock script. So the lock script controls the ownership of the cell. So in order to use a cell in a transaction, you need to be able to provide an input that makes this lock script exit successfully. And this is to enforce conditions to actually unlock that cell. And it's generally programmable, so you can put whatever kind of logic you want in this lock script, and that is part of what makes CKB so powerful. And with this comes native multisig. So if we wanted to do, say, a 2 or 3 party transaction on Ethereum, it actually becomes quite complicated to set up a smart contract to govern that. And on CKB, it's pretty straightforward to create a lock script for multiple owners. And the lock script and the type script, which I'll get into in a second, are a data structure which contain a hash of the actual logic that's going to be used and executed, as well as, that's a hash. And then this second field here, hash type, is used for references and combining of different cells into logic, which gets a little too complicated, which I won't go into here. But I want to call attention as well to the args field, which is actually storing data that will be executed within the script as an input to the script. And to demonstrate that, I can show you the default lock script. So the code hash that's used is the SEP256K1, which is actually just the code that will run to verify a signature is the proper signature for a specified owner. Now, that owner is going to be stored in the cell in the args fields, and we can see here that there's a hash of that owner's public key that's stored alongside the hash of the actual code that will verify that a signature that's provided for a transaction matches the correct owner. So this is similar to a pay to script hash in, or pay to pub key hash, I guess, in Bitcoin. And we'll update the lock script here on the example. And we'll also add in this multi-sig lock here. So yeah, and again, keeping things complete with this example. So on the left here for the default lock, that would be the code that would verify that a signature was correct. And on the right is a hash of the public key. So when the blockchain receives a signature, it's looking for a certain key to know that that is the correct value. So that would be the value that's stored in this hash of the public key. And it's very straightforward to move to a multi-sig situation. So you would have a lock logic to check a multi-sig signature, and then also a hash of the different public keys that went into actually securing that multi-signature wallet. And the next field we want to look at is the TypeScript. So TypeScripts control the logic of the cell. So they're optional. If you're just storing, say, the native token or a simple application that's just owning assets, you won't need a TypeScript. This is really to develop more application and higher level logic. And this is what state transitions are validated against. These are generally programmable, and in order for a transaction to succeed, if you're using TypeScripts, the TypeScripts on the input and output cells must return successfully, so no errors. And the TypeScript is also this script structure, and the hash type here is, there's some articles written about how you can use this for upgradable contracts, which is a very powerful feature as well. And so from here, now the Nerval's DAO cell on the right over here becomes relevant as we get into a TypeScript. And this cell just contains logic or code, I guess. And in order for any of these owners on the left to deposit their tokens into the Nerval's DAO, they need to update the cells that they're storing those tokens in with the Nerval's DAO TypeScript. And once they've done that, then the tokens are in the DAO. And in order to do that, the transaction needs to validate successfully that all of the conditions that are laid out in that Nerval's DAO TypeScript are fulfilled by the transaction. All right, so we'll add the Nerval's DAO TypeScript to these cells just for completeness. Okay, I guess I'll pause here. Does anyone have any questions on the cell or any of these fields that I've covered so far? Okay, I'll keep going. All right, so now this is kind of a formal representation of the state transition function and all the things that must be considered if you want to create a successful transaction. So we have on the left the input cells and then the output cells. And these each have the 4 fields that I just went through. And the first thing that we have to make sure of is that the input cells are unspent. So similar to Bitcoin, you can't double spend cells. And once cells have been spent, they can't be spent again. Second thing we want to make sure of is that the input capacity is greater than or equal to the output capacity. And any excess input capacity goes to a miner as a transaction fee, similar to Bitcoin. The third thing is that the lock scripts of the inputs must validate, so only the inputs. And whatever lock scripts you attach to the outputs are going to be completely fine. And the last thing is the TypeScripts of the inputs and the outputs must return successfully. And if all of this is true, then the transaction is validated, added to the ledger, and the input cells become historical, and the output cells become new cells. Now, I want to take a closer look at some things that are happening in transactions here that I haven't covered thus far. So we'll go back to this example of, say, a user depositing tokens into the Nervos DAO. I'm just going to remove the multi-signature example for now, just so this becomes a little cleaner and a little clearer. So we'll start to build our transaction here. We know about inputs and outputs. Those are pretty straightforward. But I want to bring in some new concepts. First one is DEPs, and the second one is witness data. So we'll fill in what our inputs and outputs look like, and then go over to examining what DEPs do. So DEPs are transaction dependencies, and we have cell DEPs, which are libraries. So we could have things like hash functions or signature functions. These are inputs to transactions. They are active cells, but they are different in that they can be reused. So usually an input cell is consumed in a transaction and it can't be used again, but these DEPs are read-only references. So the data that is contained in these cells when they're referenced as cell dependencies in a transaction is just read into the execution environment, and then another transaction can use those dependencies again later. The second kind of DEPs is header DEPs. So this is another unique thing about CKB, is that transactions can examine the block headers that have been confirmed previously. And this is useful for inspecting previous transactions, or the Nervos DAO uses this to get certain values out of it, out of the previous state. And right now, we'll add in that for this transaction, we need to include the SEP 256 default signature logic as a dependency. So you don't have to include this signature logic in a transaction. You could implement a new signature function and include that as your dependency. But in order to check the default signature logic, you do need to include this cell as a dependency in the transaction. So next thing we want to move on to is witness data. So witness data is an input to a transaction, and an example of witness data is a signature that corresponds to the stored public key hash. So the input that unlocks the lock script. And we'll add this here to, for completeness of our example. One thing to also note, the lock scripts and TypeScripts can access all of the transaction data. So all of the data in the other inputs and outputs, as well as the witness data. And this witness data or transaction signature corresponds to the hash of the public key that's stored in the args of the lock script of this cell. Now we need to validate the TypeScript of this Nervos DAO cell, or the TypeScript contained in the Nervos DAO cell, in order to complete this deposit. So if the logic in this cell is validated successfully, then we can add the Nervos DAO TypeScript to our output. And once this is all confirmed, then our transaction will effectively be, or our tokens will effectively be deposited into the DAO once that output with the Nervos DAO TypeScript is confirmed. And you can see that the lock script has been the same. So in moving the tokens from, say, the ownership of the user to being locked in the DAO, the lock script could be exactly the same. It's still the same key that those tokens are locked to, but the state transition logic that governs it has changed, and that effectively makes them locked in the DAO. Now, if we wanted to change this over to a multi-sig situation, it actually is pretty straightforward. So you can notice here on the inputs and outputs that the lock script has changed to be a multi-sig, but everything else has pretty much remained the same. So there isn't application logic that needs to really take into account that this is now a multi-sig. And we're just going to add a second signature to the witness data. And yeah, it makes it very convenient for developing multi-signature applications. Now I want to give an example of how powerful this construction is. So there's an application that's been growing in visibility in the community called CKB. So it's a web wallet that uses ETH addresses and creates a lock script that accepts an ETH address as an ARG to a transaction and implements the catch-at cash function that's used to derive an Ethereum address. Now, when the SEP256 signature is passed in as witness data, this cell can validate that that signature corresponds to the ETH address that the CKB or tokens are locked to. And now I'll look at a little higher level of what's happening here, and especially if we're thinking about, say, CKB compared to Ethereum. So we have this concept of a generation layer where the transaction is being constructed. So all of the cell collection, the analysis of the ledger to create a valid transaction is happening on client side. So the blockchain itself is only validating that a state transition is correct. It's not actually doing a state transition itself. So that means that on the client side, say on a web page or your phone, the application needs to be more robust than what we're used to seeing, say, with a Web3 dApp. And that application needs to be aware of more about what the current state of the ledger is. Say the example of Alice having 2 cells that have the tokens stored in them. The application needs to be aware of that. It can't just be as simple as a query call to the chain to obtain the balance of a certain account. Now, once the transaction is constructed on the client side, it's then sent to a node which can validate that transaction. And if that transaction is valid, then that node can propagate that transaction to its connected nodes. This is another difference between CKB and Ethereum. There won't ever be a transaction that fails on chain. So on Ethereum, you could have an invalid transaction that errors out, but on CKB there will never be an invalid transaction that's included in a block. It just will never make it past validation. And building on that point, other differences in terms of the execution model, say if you're thinking about building an application, it becomes really important to understand, say, this concept of, say, like cross-contract calls or interactions between different scripts and pieces of state. So this is the usual model that I think that most smart contract developers are used to seeing. You have a signed transaction that touches a particular contract, and this is Ethereum, by the way. Then that contract can call into another contract that maybe calls back to the contract that called it. That contract can then call into another contract, which can call into another contract, and finally the state is updated and the operation exits. Now on CKB, all state changes are explicit in transactions. This is part of how we can make the statement that there'll never be any failed transactions on chain. So this is an example of what these explicit dependencies look like. You could have a transaction that creates outputs that are then consumed as inputs in a transaction in the same block. That's one way of kind of connecting transactions together. There's also this concept of an open transaction. So in this example, Alice will provide an input and sign a transaction that includes that input and also, say, 3 outputs. And Bob can come along and sign a transaction that includes his inputs and the same 3 outputs. And these transactions can be combined together and then accepted by the chain. So you have these two users kind of collaboratively creating a transaction. Another difference is in resource metering. So this is also called, people are very used to calling this gas because of Ethereum. So gas is a unit of measure for storage and computation. And a very prolific dev described his experience of gas costs is usually dominated by storage costs in my experience. Now, on Nervos, this changes because storage and computation costs are separate. So CK bytes are used to store data on chain. So users actually own portions of the ledger state. So if I wanted to store, say, a piece of code that took up 100 kilobytes, I would need to own 100,000 CK bytes to have that space. And then cycles are used for computation. Now, because of what's been described as storage being this thing that's always a consideration in Ethereum, separating out storage from computation in terms of an application may actually make applications that were not feasible on Ethereum actually possible on Nervos. So I would say to open your mind and experiment to things that maybe you hadn't tried out before because they were just impractical on previous blockchains. And I'll wrap this up just by providing how we construct a transaction. So you'll compute a transaction hash from all the fields below, or I guess all fields that go into a transaction excluding the witnesses. There'll be a signature provided on that, and then append the witnesses to that, and then that will be sent to a CKB node for validation. If the transaction is validated, then it will be propagated to the rest of the peer-to-peer network. So with that, I'll open up to questions. Appreciate your time.
How do I know which depths to use in a transaction?
Depending on the functionality you require, is there code that's needed to execute your transaction that is not included in the inputs?
Okay, so like if a script is attached to a cell, then I need to include that script in the depths, is what you're saying.
The script, yes.
Okay.
也可以用中文提问，然后我们翻译一下。All right, no questions.
Okay.
So do we have Tanner at the next step, next part?
There's a question from Williams in the Zoom chat.
Okay, let me check. So any advantage for uncertain transactions? Well, I wouldn't describe the transaction as uncertain. The transactions are more certain because you have to specify that these are the inputs that produce a certain output. So you can think of the example of, say, front running a specific trade, say on an account model chain, where that transaction that gets the transaction that gets pushed back because someone front runs it to take that trade. That transaction that was moved actually will still execute. So I think there's trade-offs to each model, but the cell model definitely provides more certainty that a transaction will only execute if the parameters that it was created under stay the same. If anything changes, say if the input cell gets spent, then that transaction is just going to fail before it reaches the chain. But Kevin, to your question, Tanner is going to cover the node and SDK setup in the session tomorrow.
Okay. Well, I think if there are no more questions, then we're done.
Okay. Thanks, everybody.
Thanks, Mo.
Okay. All right. So tomorrow at the same time, we have Tanner talk about more details. Are you gonna give an overview of what you're gonna present tomorrow, Tanner?
Yeah, sure. So basically going to go through, so some practical stuff on setting up a programming environment for CKB and building some dApps on there, and kind of a high-level mental model and workflow for translating logic into CKB specific logic, and then go through the token standard and actually build some generator, build some issuance and minting and transfer with the validation scripts, like the lock and type scripts Matt talked about, and then also the generator code to submit the right transaction. So more programming and showing, okay, if you want to develop an app on CKB, you open your editor, where do you go from there, basically?
All right. So we look forward to that tomorrow.
All right.
Awesome. Thanks, Matt.
Thanks.
Thank you. Thank you, everyone. Bye.